In this guide, here is the concrete technical problem GNAP solves. GNAP works as a four-step stateful transaction. Let's look at what GNAP looks like on the wire, and four developments are shaping where GNAP goes from here. Identity expert, powering you to be an expert in identity. OAuth 2 is 13 years old. In that time, it has grown from a single RFC into a sprawling family of more than 20 specifications. PKCE to fix the authorization code flow, PAR to protect the authorization request, RAR to express rich resource descriptions, DPoP to sender constrained tokens, JAR to sign the request object, CIBA for decoupled authentication. Each extension was a patch on a framework that was never designed for what we now expect from authorization. Today we are covering GNAP, the Grant Negotiation and Authorization Protocol, standardized in RFC 9635 and published by the IETF in October 2024. GNAP is not an extension of OAuth. It is a ground-up redesign of delegated authorization, a single JSON negotiation endpoint where the client describes what it wants, who it is, and how it will prove possession of its keys, and the authorization server decides how to interact with the user to fulfill the request. Resources, subjects, key proofs, and interaction modes are all first-class fields in a single transaction. No scope strings, no grant type selection. One protocol, not 20. Think about a valet key versus a smart contract. When you hand a valet a key, you hand over a physical object that unlocks your entire car. The valet can drive it anywhere, open the trunk, and you have no way to audit what happened. When you want the key back, you have to find the valet in person. That is OAuth 2, a bearer token that grants access based on a scope string, tied to a static client ID registered in advance with no native way to express exactly what resources you need or to rotate the key without starting over. Now imagine a smart contract. You specify precisely what rights you need, read this folder, initiate a payment of exactly this amount, access this API for the next 24 hours. The counterparty negotiates the terms. The resulting agreement is cryptographically bound to your specific key pair so nobody else can use it. You can modify or cancel the agreement mid-flight. That is GNAP, structured access descriptions, a stateful transaction the client can continue or cancel, and every request signed with a key the client proved it controls. The valet key model required you to trust the valet with everything. The smart contract model lets you grant exactly the minimum access needed, bound to the key that you hold. Here is the concrete technical problem GNAP solves. First, OAuth 2 has no native way to express rich resource descriptions. If you want to initiate a payment of $500 to a specific account, you stuff that into a scope string or bolt on rich authorization request from RFC 9396. GNAP makes structured access objects a first-class field in the grant request, no extension needed. Second, the implicit flow was deprecated in OAuth 2.1 with no clean browser-based replacement for single-page applications that cannot keep a client secret. GNAP's key-bound transaction model is designed for public clients from the start. Third, OAuth has no native key rotation. A refresh token cannot rotate the client's key, you need a new authorization. GNAP's token management URI on every issued token gives the client a dedicated endpoint to rotate, revoke, or introspect tokens without a new grant flow. Fourth, dynamic clients in OAuth require either pre-registration or a complex dynamic registration flow. In GNAP, a client describes its key and display metadata inline in the grant request. No pre-registration required for low-assurance scenarios, with attestation-based trust for high-assurance ones. These four gaps, rich access, public client proofing, key rotation, and dynamic registration, are the primary design drivers behind GNAP's architecture. GNAP works as a four-step stateful transaction. In Step 1, the client posts a grant request to the authorization server's transaction endpoint. The request carries four key objects: access, describing what tokens the client wants and exactly what rights they should carry; client, containing the client's public key and display metadata; interact, listing the interaction modes the client supports such as redirect, user code, or push; and optionally subject, specifying the identity claim formats the client wants in return. The entire request is signed with the client's key using HTTP message signatures. In Step 2, the authorization server responds without issuing a token yet. It returns a continue handle, a URL plus a key-bound continuation token, and an interact block telling the client exactly how to involve the user, a redirect URI, a user code, or a push notification. In Step 3, the user authenticates and consents through the chosen channel. On completion, the authorization server generates an interact hash, a value derived from both the client's nonce and the server's nonce, and returns an interact reference to the client. In Step 4, the client submits the interact reference to the continuation endpoint, signed with the continue token. The server verifies the hash binding, confirms the interaction maps to this exact grant request, and issues the access token keybound with a manage URI for future lifecycle operations. Let's look at what GNAP looks like on the wire. The client posts a JSON document to the transaction endpoint. The access array contains structured objects, not scope strings, with a type field, an actions array such as initiate and status, a locations array pointing at the resource server, and arbitrary API-specific fields like the payment amount and creditor account. The client block embeds the client's public key as a JWK along with the key proof mechanism, in this case HTTSig, meaning HTTP message signatures per RFC 9421. The interact block declares redirect as the supported start mode and provides a finish block with a redirect callback URI and a client-generated nonce. The authorization server responds with an interact object containing the redirect URI where the client should send the user a finish hash value to verify on return, and a continue object with a URI and its own key-bound access token. The client must hold state connecting its nonce to this continue URI. After user consent, the client posts the interact reference to the continuation endpoint, with the continue token in an authorization header also signed. The final access token response includes the token value, a manage URI for rotation and revocation, the structured access array mirroring what was requested, and a key. True flag confirming the token is sender constrained to the client's key, meaning only a holder of that private key can use it at the resource server. Let's walk through GNAP's key threats. The first and most GNAP-specific threat is interaction reference substitution. Unlike an OAuth authorization code, the interact reference in GNAP is meaningless without the hash computed from both parties' nonces. An attacker who intercepts the redirect and swaps the interact reference cannot succeed because the hash will not verify. But a client that skips hash verification will happily continue an attacker's grant, giving the attacker a valid token. Always verify the hash. The second threat is continuation token theft. The continue object returned in step 2 carries a key-bound token. An attacker who steals it cannot use it without also holding the client's private key because the continuation request must be signed. The mitigation is proper key storage, hardware-backed keys where possible. The third threat is client impersonation. A rogue client presents the same access request as a legitimate client, hoping the authorization server will issue equivalent tokens. GNAP mitigates this through key binding in the grant request. The AS validates the key proof on every call. For high-assurance deployments, the AS can require pre-attested client keys or certificate-bound identities. The fourth threat is authorization server metadata spoofing, an attacker serving a fake transaction endpoint. The mitigation is HTTPS with certificate pinning, OAuth server metadata discovery, and DNSSEC where available. Do not allow clients to accept dynamically discovered transaction endpoints without a trust anchor. 4 developments are shaping where GNAP goes from here. First, RFC 9635, the GNAP core specification, was published by the IETF TXAUTH working group in October 2024 as a proposed standard. RFC 9767, covering GNAP resource server connections and defining how authorization servers communicate token metadata to resource servers, followed shortly after. The core protocol is stable. Second, the TXAUTH working group is actively drafting GNAP multi-owner resources, which extends GNAP for scenarios where a single resource has multiple owners, the primary use case being healthcare records shared across providers and patients, and financial accounts with joint ownership. Third, GNAP and rich authorization requests from RFC 9396 compose naturally. GNAP's access array subsumes RAR semantics natively. The structured access object in a GNAP grant request is effectively a RAR authorization details object as a first-class field. Expect financial API profiles to formalize this composition. Fourth, the most prominent production GNAP deployment today is Interledger's Open Payments Protocol. Major identity vendors are tracking GNAP but have not shipped GA support as of mid-2026. Adoption is expected to lead through FAPI-adjacent open banking ecosystems once interop profiles stabilize. If you are designing a greenfield authorization system today and you control both the authorization server and the clients, GNAP gives you one clean protocol instead of OAuth 2.1 plus 5 extensions. Subscribe to Identity Expert so you don't miss AuthZen, the OpenID authorization API, coming up next. All primary sources cited in today's guide are listed on screen. You'll find direct links to the RFCs and specifications in the video description below. If this breakdown helped you understand the topic better, please subscribe to Identity Expert. We publish a new protocol deep dive every week. Thanks for watching. If there's a specific identity standard, authentication flow, or security protocol you'd like us to cover next, drop it in the comments below. We build our content based on what the community asks for. Subscribe and hit the bell so you never miss an episode.